First of all, very good morning, and it is 17th. First of all, let's quickly recapitulate what we have seen last time. Yeah, not much, but we have seen a few things. We started off with what? We have started off with complements of, subtraction using complements. We have seen that there are two methods. There are two types of complements. Which are those? First, close your notebooks. Okay, you close your notebooks. So this R's complement and R minus 1's complement. R's complement is called radix complement, and R minus 1 is diminished radix complement, just because it's one less than that. We have seen that the methods differ only if when the carry is generated. We found that in R minus 1's complement, if the carry is generated, then you do the end around carry operation. If it's not, if it is the R's complement wala thing, okay, you simply discard that carry. Okay, whenever the carry is generated, okay, you do this operation and you will get the correct answer. Whenever the carry is not generated, the answer is in R minus 1's complement or R's complement, whichever the method you are into. Yeah, yeah, but yes, that's important, and with a negative sign. The answer is not in correct one, the answer is negative. That's what we have seen. Then we have introduced the idea of logical thoughts. We have seen that the logical thoughts can be expressed more or less with a binary variable. Okay, we have defined it as Boolean. Okay, just because he was the one who coined these terms. So the Boolean algebra has come out, and we have defined a set of rules, isn't it? We have defined a set of rules around 31 rules we have quoted, isn't it? So keep those rules as a as a bookmark for you, because sometimes you may need like how we have come down to an expression using such rules. So please bookmark that page wherever you have written those things, because that will help you out in minimizing the things. All right. so so we stopped where when the rules were defined, right? So let's proceed. Now, see, we have given some examples of any function. Say, for example, I've given some example of, say, you know, if I need to continue with the lecture, I've given an example that if I'm having sufficient energy, then only I will continue the lecture and so on. Then, how many possibilities of such functions were there if there are two variables? We have seen that. Huh? For two variables, yeah, for two variables, how many such possibilities were there? Possible expressions to the power 2n, right? So total, 16 different possibilities of logical expressions were there. So those logical expressions can be anything. Like we have seen that if x and y are two variables, it may be xy plus x bar y bar that we have seen. Okay. Now see, I'm doing this in a prime or bar. I am putting whenever this function goes 0, whenever x is 0. Okay. Now such functions. Okay. Let me define some terms. Say if x is there, now this each variable, any variable in a complement or uncomplemented form is called as literal. It's any variable in complement or uncomplemented form. What is complement? As we are now dealing with, we are well convinced that we shall be using binary as a base, okay, 2 as a base. Complement is simply, change 0 to 1 if the values are there. If the values are there, so let me define the complement first. The complement of values, okay. So just exchange 0 with 1, okay. So values. If it is complement of an expression, apply De Morgan's theorem. Yes. Literal is any variable in complement or uncomplemented form. Yes, so that is only one variable is known as a literal. Say for example, this term is having two terms with four different literals. See, the literals may be repetitive also. Say for example, I may take an expression x bar y plus y bar z. So still there are four literals. Okay, I mean in the original function you may say that this has been repeated, but in untouched format. Okay, original expression is having four literals. Okay, a variable in each term maybe in a complement form or in an uncomplemented form. That is known as literal. I'm just defining these terms because these terms will be required in the subsequent sections. Yes. We can take y bar. No? Not term is called as literal. A variable. I have said as a variable, not a term. So here the difference is this is term. This is term. This one is a literal. This is a literal. This is a literal. That is a literal. A variable, any variable, a variable. Okay, in complement or uncomplemented. If you remember this, in the last class we have quoted 30 different rules of Boolean algebra. So I think at the end, rule number, can you tell me the rule number? I have specified them as De Morgan's theorem. Which were those? You tell me those theorems. X. You should not say dot. So and. Okay. Whole bar? You should say whole bar. This is as good as x bar or y bar. Now see, plus if you say it has two meanings, we have also seen the difference. Okay, the arithmetic plus is different from logical plus. Okay, this is the difference. What we are saying here is logical things. Okay, logical set of rules. Tell me the another one. There were two De Morgan's theorem, right? So always remember these rules. These are known as De Morgan's theorem. Can you quickly prove them? How to prove them? See, there are many ways to prove them. Okay. So what you can do is, the simplest way would be, by induction. That means what? You take all the possibilities of x and y, just compare left hand side and right hand side. If the truth tables are turned out to be the same, okay, they are equal. Okay, you can verify. It's simple. So homework for you to verify this theorem. Verify using induction. इंडक्शन मीन्स कू करनी ये वेरिएबल्स की ऑल पॉसिबिलिटीज लो वॉट एवर द आउटपुट इज देयर यू जस्ट कंपेयर लेफ्ट हैंड साइड एंड राइट हैंड साइड एंड by expression by using other boolean and theoretical. All right, so I mean if you closely have a look at this, what does it say? Wherever the AND operation is there, replace it with OR. Wherever the AND operation is there, replace it with OR. Wherever OR operation is there, replace it with AND. And okay, the literal, okay, which was in the uncomplemented form, you complement that. Okay, that is what a complement of an expression says. Okay, so complement of a values would be simply replace 0 and 1. If it is the complement of an expression, you simply follow this De Morgan's theorem. All right, yeah. So for an example, you take this example. Take complement of x. Can you find the complement of this? It's easy. You just put a, whenever the expression is there, okay, complement means f bar. Always remember. The representation of complement is a bar or a prime. I can also represent it with something like this. It's called f prime or f bar. Okay, both are the same. Whenever the complement is asked, just put a bar there. Okay, so a plus b plus c, a total bar. What it would be? What the De Morgan's theorem says. Now De Morgan theorem, okay, please note that De Morgan theorem is valid for any variables. I mean any number of variables. Homework for you to prove that. Okay, what I am saying is De Morgan's theorem is valid for any number of variables. Prove that. Simple. So a bar, now always this bar is getting distributed all over, okay, and wherever the or is there, you replace it with and. B bar and C bar. See, there is a difference between AB bar and A bar B bar. नहीं आजू बाजू में रहते तो बार जोड़ दिया मैं. No. See, whenever in the exam also, if I find any kind of ambiguity between the distribution of this bar, okay, I'll straight away give 0. It should clearly reflect that A is bar is there specifically on A. So these two are not equal. Okay, these two are not equal. Say A and B is 0 and 1. You first and then take the not. Now I have given you the preference of operations, logical operators. First it is the brackets or parenthesis. Okay, I should not say brackets, parenthesis, then not. Okay, not I haven't told, but not and then or. So first you will be in not. I mean, it's not is defined for two, not for two. First you distribute this. First operate the De Morgan's theorem. Apply the De Morgan's theorem. Say for example A and B as 1 and 0. The product of them will be 0 and complement of that will be 1. Here, if A and B are 0 and 1, still it would be 0. But what if it is 0 and 0, or 0 and 1, or 1 and 1? See, it's not necessarily that these two will be equal. These two will be same. Okay. So what I'm saying is De Morgan's theorem is valid for all number of variables. Just need to if it is complement, you just apply De Morgan's theorem and just replace and with or and complement those things. Take another example. Say for example, take this. Find complement of if f is x y bar z bar plus yz, f dash equals to what? You find it. Do that. F equals to x into yz bar. I'm making some change. Z bar equal to what? How to proceed with? Have you done? I mean, just try it out. Now you'll get. See, these two are getting. Okay, it's a bracket here. See, I have made changes here. These in the bars are different. Okay, here individual bars are there. If the bars are common, can you check the expression turns out to be the same or not? You go step by step. Say for example, you take this expression. F bar, how much it would be? Bar on whole thing, right? Z bar separately. Put a bar whole. Apply De Morgan's theorem. What does it say? Whether the and is there. So it will be x bar plus, tell me, y bar, z bar. What should I do? I mean, if I need to distribute that, okay, let's go one by one. Plus yz ka whole bar What is that? X bar plus, now you tell me. No, y. Uh, wait a minute. Wait. Let's go step by step, no? Into, is that okay? X bar plus, now you tell me. Y or Z into y bar. Is it okay? Now, no? कहाँ पे? ये वाला ले रहा हूँ मैं, ये वाला आएगा तो अलग आंसर आएगा, इसलिए मैंने 2 दिए। अब ये सॉल्व करो, अब आप वो सॉल्व करोगे, ठीक है? Do the same thing with here, okay? You'll come to know why these 2 bars are different. How does it make difference? You solve this one, the second one. Solve this. Apply De Morgan's theorem step by step. Okay. So out of 30 different properties or axioms, we have simply used 2 of them. Okay. We may take advantage of all of them. We may use many of them. Okay. It's up to you. So our job here is always minimization. You always remember, here we are not doing any kind of minimization. I've simply demonstrated what a complement does. Okay. Now let's take some examples. Solve this, okay? Solve this. Take this example. XYZ or X bar Y or XYZ bar. How many literals are there in this? You tell me. How many terms are there? First of all, you tell me. How many terms are there? Wait, terms. 3 terms. Term 1, 2 and 3. How many literals are there? This is 1, 2, 3, 4, 5, 6, 7, 8. So 8 literals. Okay. Maybe repetitive. So the job is to reduce. Okay. To reduce this expression, let it be f. Okay, f equals to expression for f to 1 literal. Can do that using not De Morgan. De Morgan is anyway not required here, guys. I haven't said any to take the complement. Okay, complement, I just wanted to demonstrate the complement. While doing the complement of an expression, you need to go for De Morgan's theorem using any axioms of Boolean algebra. Okay. Next. Now you just bookmark that page. Okay, the 30-31 properties, whichever I've told in last class, you just bookmark that page. Okay, always remember that, because with practice you will come to know. But just time being, just bookmark that page and use those axioms of Boolean algebra and reduce this to 1 liter. Can you do that? Quick. Reduce it to 1 liter. See, just to begin with, see whatever the common, and just see my aim is to make this expression as compact as possible. Okay. So here it is, xy here, xy there. Can I combine these two? And I may use the property of what? XY and Z or Z bar. This goes off because any variable or variable ka complement will be 1, and so on, plus whatever that is, x bar y. Reduce it to 1 liter. Do that quickly. If you are done with that, okay, I'll give you some more. Take this example, a bar, this b bar plus c bar d plus b. If you have doubt, please ask. C d. Do that. वन लिटरल मैन, मैंने बोला कि वन लाओ करके, जबरदस्ती मत लाओ. यस, reduce this to 1 liter. Literal is nothing but a variable in complement or uncomplement form. These words are taken from English. Okay, अभी से ना literally मैंने ऐसा देखा था, means what? सच्ची मैंने ऐसा देखा था. Okay, literal means each and every, it means, I mean it. Okay. Each and every letter. All right, those who are done with that, go for this. X bar y bar plus z ka bar plus z plus xy plus wz. Oh my god, now more number of variables. Okay, reduce it to 3 literals or as many less literals as possible. I'll say minimum. Now minimum some may get 4, some may get 3. So whoever wins, okay, they'll get marks. Minimum literal. All right, I was able to reduce this to 3 liters. Okay? So you may go down to 2, 1. Let's see. All right. So we have seen the. Is it okay? I should show. This was one of the feedback. आप चेंज कर देते हो, रखना चाहिए था. ठीक है, देखो. Need to cover a few things today. Buckle up. See, sometimes what we are doing here, we are making maximum use of which property? Which property did we use here? Huh? Yeah, but not only that property, we have used distributive property also. We have used distributive property, we have used that. Huh? What was that property? X. Yeah, that one. We have used two properties here. It's not necessary always that we'll get a compact expression only by combining these things, only by distribution. We may expand sometimes. See, sometimes intuitively it may happen that we may expand a bit. Like this expression is given, I may expand this expression of with some more variables, and then we may get even better or reduced form of an expression. I'll demonstrate that. Wait, I should get some example like that. Alright, we'll see it later. So, yeah, what we have seen is a literal. What do you mean by literal? And we have seen that an expression may have some different forms. Let's say x plus yz. It may have some different forms, or okay, this one. F2, it may be x bar or y bar, z bar, anything. Okay. Now, see, there are various ways to express these Boolean expressions. Okay, but what are standards, or what are said to be a proper form, are known as canonical or standard forms. So let's discuss canonical. standard forms of Boolean expressions. I'm just giving examples that any function can be expressed in various ways. Say for example, an expression may be 1. Okay. An expression may be f3, or an expression may be x plus xy plus xyz bar. Anything it may be, right? But there is specific format, okay, or a specific form which are said to be standard or canonical. We are discussing those forms, okay. I mean, if we express any Boolean expression in such form, it will have a unique expression. Okay, so canonical form or standard forms means each and every literal should be covered in each and every term. Okay, so that's the thumb rule. So let me code this. Say for example, first take any variable. Let's say it's x. There are two possibilities. It may be available in x, or it may be available in x bar. What if there are two variables x, y? There are 4 such possibilities. It may be x, y, it may be x bar y, x y bar, or x bar y bar. What if there are 3 such possibilities x, y, z? You will have 8 such combinations. So each of those combinations, okay, now let me note, each of this possible way of what is called as AND expressions, each of this product term, okay, which covers all these variables, isn't it? I mean, in this term all the variables, both of these variables are covered. Say for example, I am taking this one, okay, it will be x bar, y bar, z bar, okay, x bar, y bar, z, and so on till x, y, z. In each and every term, okay, every variable is covered, okay, either in complemented or uncomplemented. Each and every term is having literals covered. Now these terms, okay, when you express it as now let me code this term. These terms, okay, are called min terms. So when a function is expressed, say for example it's x, y, z, or x bar, y bar, z bar. Each of this term, whenever it is expressed as a product, okay, as a sum of products, then each of this product is called as a min term. Okay, min term. Okay. Condition being each and every term must have all the variables. Okay, so that form is known as canonical sum of products, or sum of min terms, you can say. This is one way of expressing any Boolean function. Okay, this is a min term. Another standard form is a max term. Say for example, there is a function x, y, z. See, what is the idea behind this? Say for example, now let me rub this first. The idea is, say for example, there are n variables. There are 2 to the power n possibilities of the expressions, right? I mean, a literal may be in a complemented or uncomplemented form. So there are 2 to the power n such possibilities. Okay, these possibilities may be for the AND expressions or maybe for OR expressions. See, we have seen that in Boolean algebra there are only three basic operations: AND, OR, and NOT. Okay, there are no other operation, basic operations. So 2 to the power n possibilities for AND, and there may be also 2 to the power n possibilities of OR. What about NOT? We have already covered in the literals. Okay, so 2 to the power n possibilities of or. So if it is 2 to the power n possibilities of AND, they are called as min terms, and if it is for OR, it is known as max terms. So to give an example, it would be F, if it is X or Y or Z, product X bar or Y bar or Z bar. Okay, these are two terms. Now it is product of sum. Okay, it's a reverse way around. Okay, it's a product of sum. मतलब पहले sum लो बाद में product of sums. Okay, each of this term is called as max term. What is the criteria? Each of this term must cover all the variables either in complement or uncomplemented form, and it should be expressed in this form, a product of sum. If it is the case, then it is known as a max term. If it is the other way around, okay, it's a sum of product, it's called as min term. Now, let me take an example of three variables. Let's say it is X, Y, Z. If there are three variables, how many possibilities? 2 to the power n? Not 2 to the power 2n. 2 to the power 2n is what? I mean the Boolean expression ka possibilities. You tell me. 0, 0, 1, 0. Now let me quote the decimal equivalent of this as j. Okay, there is a meaning for that. Let me write as 0, 1, 2, 3, 4, 5, 6 and 7. When expressing, okay, now there are 2 to the power n such possibilities for three variables. Now how many there are 2 to the power n possibilities of min terms and max terms. Okay, so the min terms, okay, let me write that. The min term is expressed when you make a variable prime or a bar if it is 0, you keep it 1 if it is if you keep it unprimed when it is 1. Okay, say for example this is 0, 0, 0, you take X bar. Now you tell me it's min term, no? Product Y bar, Z bar. You tell me here X bar, Y bar, Z. You make this variable prime or bar only if it is 0. Okay, so it is now let me X bar, Y, Z bar, X bar, Y, Z, X, Y bar, Z bar. Now you might have got the idea that how many possibilities would be. Now each of these are known as min terms. Okay, X X, Y bar, Z, X, Y, Z bar, X, Y, Z. Now they are indicated as this. Okay, now they are denoted, expressed as small m. Okay, small m with a a subscript of j. So this becomes m0, m1, small m. Okay, small m, m2, m3. Now as I said, okay, there is also possibility for max term, right? So max terms. That is represented by capital, okay, capital M with a subscript J. What is J? J is the decimal equivalent of the corresponding binary expression. Yeah, so it is represented by capital M 0. You tell me. Now in max term, it has to be the product of sum. Okay, I mean there is no product, but each term is expressed as sums. Okay, But okay, the rules are reversed there. Okay, you do the variable prime when it is 1. Okay, the reverse way around. Okay, here we have made the variable prime of bar when it was 0. Here it should be the other way around. Okay, we should make the variable prime only when it is 1. So what is the expression here, you tell me? Yeah, so x, you should not take bar, okay, just because it is max term, z. Go on, m1 x or y or z bar, yeah, m2 x or y bar. Whenever 1 is there, you make it bar, okay, for max term. Yes, please. Which one? This one. Okay. Oh my God. Okay. Fine. So that's a thanks for homework. So homework for you is why these terms are called max terms, why these are called min terms. I was about to tell, but do some brainstorm and why these terms are called min terms and why it's called as max term. Not because it is 7, it's called as max term and min term. Min terms are the expressions. The expressions, okay, expressed as standard products. What do you mean by standard products? The product should cover all the variables either in complement or uncomplemented form. Okay, but all the variables should be covered or must be covered. Okay, if that is the case, each and every term is known as a min term. The other way around would be if I consider all the variables as a standard OR. Okay, that means all the variables should be covered either in complemented or uncomplemented form, but in OR form. Okay, that is called as a max term. Okay, the reason behind that you have to find out. Find out, the homework for you is to find out why these terms, although these are product, why this is called as a min term, although these are the OR, why it's called as. And you will come to know in the subsequent lectures why it is called. But if out of curiosity you may find it out why it is called as a min term. That's not a reason. This is always 0 and always. How? Min terms are all ones. Then it should be max. They should be called as max term then. Why it is called as min term? See, I'll give you an example. Okay. This is a glass of water. Half knowledge is always dangerous, isn't it? If you try to pull the water in this, it will fill out. You come up with an empty glass so that water can be filled. You got what I'm saying? Okay. See, you just find it out. Why it is called, technically why it is called as min term or max term. That's a homework for you. All right. So let me write the other expressions. So it's x plus y bar. Just complete this. Z bar m o x bar y z and 5 x bar y plus z bar and 6 x bar y bar z and 7 x bar y bar or z bar. So this is homework for you. All right. So, so this is denoted by capital M and J. Okay, that is covered. Now, all right. You may have seen. Always this is true. What the min term with a subscript is always a complement of a max term with the same subscript. This is always going to be true. Another way of it, now let me, the fact is any Boolean expression can be represented in sum of product or product of some form. If it's not, you can always express or convert it to standard form. When I say standard, there are only two forms, okay, sum of product or product of sum. Now whenever I say that, okay, we assume that whatever the Boolean expression you have been given is in some standard form. Say for example, an expression is this one, let's say x yz or x bar yz. This is one way of expressing any Boolean expression. Another way is, this is also this. Now this is sum of min terms, right? This is min term. When I say min term, it should cover all the variables. It should be in sum of product form. It may also be expressed as m. Now you tell me the decimal equivalent of this. Okay, it's 111, so it becomes m7. Or you tell me for this m3. This is another way of expressing. Another way of expressing would be using this one. Okay, sum of, now I mean I'm simply using some compact expression, 3 or 7 or 7 or 3. It doesn't matter. So this is the way you will get the expression, or you will get a problem. Whenever I say f equal to sum of 3 comma 7, you should get to know that, okay, it's actually x y z. It's a, yeah. So how to express, the best way would be f, the variables in use, x y z equals to sum of 3 comma 7. This is a more compact expression. Yeah, I don't need to repeat x y z always. Or it would be m3 plus m7. If it is max term, okay, just write on top. If it is max term, say for example f of x, let's say if it f equals to x or y or z, let me put bars anywhere, in x, y bar or z. You tell me what this. Now this can be expressed as, now you tell me. Huh? M, capital M. What is this? No, 0, 1. Wait. This is 101. How much is that? And what should I write here? Product. So product of sum. It's a dot. M, you tell me. This is okay. A more compact form would be f of x, y, z equals to product. Okay, product is this one. Or you tell me 5 and as simple. Okay. Should interpret this expression as this one. All right. Take this example. Let's say this. Let's say f1 equals to 1 4. Okay, I should not write those. X, y, z as 147 and f 2 as five, 6, 7. You write the expressions, express this in min term and max term form. Okay, as I said, okay, yeah. One more thing, and I didn't tell, but inherently it comes. These min terms are formed by combining all ones, and max terms are formed by combining all zeros. If you form a truth table for this, you form a truth table. This value is, now when I say it's min term 147, it says that, okay, the value f1 is true, that means 1 only for combination of 1, 4 and 7, decimal equivalent of 147. Whenever if I specify this product, okay, say whenever I say this, okay, this expression is false, okay, that means 0 for 0, 1, 2. That's the meaning, right? I mean, we have interpreted those expressions like that, right? See, see here, whenever I say, this m, small m as, let's say it is, this, you take that example, form a truth table, and express both the functions, in min term and max term form. Do that. Form a truth table out of this. You simply ignore this. Form a truth table. What is truth table? The truth table means you put all the possible combinations of the input variables, check for what possibilities, and the given expression is true. Okay, accordingly you make the values as zeros and ones and express the variables. Do that. Whose lecture is there? Huh? So what is it? Okay, let me quickly 0, 1, not able to, want some more time. Okay, so f1 is true for 1 with 1 here, then 4 here. Okay, I can mark this. Seven. Rest it is. What about the other one? 3. Let me write the J also. J. 0, 1. Yeah, this is 3, 5, 6, 7. Rest are all. I have done that just because this was expressed in min term form. Okay, if that would have been in max term form, okay, the procedure would have been, I have made first zeros and then rest of them as ones. What I am saying is any expression, let's say this is the expression, f1 is the expression. You tell me the min terms for them. F1, you tell me. Yeah, x bar, y bar, z, or you tell me x, y bar, z bar, or yeah, x, y, z. What I said, this is in what form? Sum of products. Okay, SOP form. Like I said that any expression can be formed. This is the same expression can be expressed as product of sum also. Okay, How is that? By combining all zeros, you take all zeros and express it as sum of product of sums. Say for example, you take all zeros. What is 0 here? Okay, instead of combining 1, I'll combine 0. Okay, so f1 would be, you tell me now, x or y or z product with, you tell me here, x or y bar. Okay, just because the rules will be reversed here, or z, you tell me next, x or z bar, fourth one x bar or y or z bar, another one x bar or y bar or z. Okay, what I'm saying is these two are equal. Which one? This and this is equal. Homework for you, prove that. How? I mean, no sir, once के जगह हमने zeros combine कर लिए तो ये equal. Mathematically, okay, with Boolean algebra, prove that these two are equal. Alright, okay, so so let's stop. So so this is a min term form SOP and this is max term form US. Product of sums. The homework is to prove this. Prove these are equal. See, till now you might have learned that ठीक है, equal होते हैं, मतलब you might have assumed some things and went, but I want explicitly to prove this. See, I mean, you begin with one expression, you derive the another, you begin with another, you derive the one. Or you may take reference of this truth table. That's the easiest way. Take the reference of this truth table, okay, and go ahead. Alright, so let's stop here.